Hello, BC Calculus students. This is Mr. Johnson, and this is section 3.1, which is on derivatives of polynomials and then exponential functions. So this is all review material from AB Calculus, and this section is a pretty quick section. So let's talk about just our general derivatives here for polynomials and exponentials. We have our derivative of a constant, which is going to be 0, the derivative of x, which is of course 1, and then your general power rule, which says that you bring the power down and you multiply by x to the power of n minus 1. If you have a constant times a function and you want to take the derivative, you can simply just take that coefficient there and multiply by the derivative of that function. If you have the sum or the difference of two functions, you can take the derivative of each function and then just take the sum or the difference, except add a g prime there. Of course, the derivative of e to the x, one of the most common ones that we end up using, is simply just itself. And then the derivative of a to the x you learned last year, but it wasn't used very often. It's a to the x ln of a. Keep in mind that the derivative of e to the x does fit into this a to the x category, but if you were to take the definition of the derivative of a to the x, you would get e to the x ln of e, and since ln of e is 1, that's why we end up getting just e to the x. Okay, let's try just a small number of examples here to review, again, your derivatives of polynomials and exponential functions. So this first one is actually utilizing the definition of a derivative, and if you remember back to when we were talking about this limit definition in the past, we have the limit as x goes to a of f of x minus f of a divided by x minus a. So our task here is to identify what f of x function we're dealing with in this particular problem, and then also identify what the a value is, because this definition of a derivative says that we end up getting the derivative of f at a. So the function a, or excuse me, the function f of x is going to be written in the problem right here in our general definition, which means that that lines up here for e to the x. So our function is e to the x, and then we have to try to think through what a could be. Now, in the denominator, we have just x written. However, the definition says x minus a, so that sort of implies that a is 0. If we go up and look at the problem and we see a 1 here, does that follow that, if we have a function e to the x and a is 0, would we happen to get 1 there? And the answer is yes, because e to the 0 would be 1. So it appears as though a is going to be 0. So with all that information being said, we want to calculate f of a, or excuse me, f prime of a. So we have f prime, which is of course just e to the x, and then we would evaluate this at f prime of a, which is f prime of 0, and that gives us simply just 1. Now, as a quick review, and we're not going to talk about L'Hopital's much in this chapter, however, I'm going to bring it up occasionally, especially in a case like this, where I think it's really helpful. But L'Hopital's rule is one of the applications we have of derivatives for limits. And remember, when you're analyzing, and I'll just kind of do this off to the side here, so when you're analyzing a limit, your first technique is by substitution. So if you were to plug in x is equal to 0 here, you would end up getting e to the 0, which is 1 minus 1. So you would get 0 in the numerator, and then of course 0 in the denominator. So with L'Hopital's rule, if we're able to explicitly write our limit of the numerator as 0 and the limit of the denominator as 0, then we can apply L'Hopital's rule. And L'Hopital's rule says that we take the limit, we do not change anything about how the limit approaches a certain value, but we take the derivative of the numerator, which is e to the x, the derivative of the denominator, which is 1, and we simply apply substitution again, and we get 1 right away. So if you're working on this kind of a problem, and let's say it's the AP exam itself, and even showing work is not something that's necessary, L'Hopital's rule is really fast. Even if you need to show your supporting evidence like you do for our class throughout the year, using L'Hopital's rule is certainly a technique you can utilize, and sometimes it's a little bit faster. Okay, let's try example 2. So in this problem, we have a piecewise function, and we want to identify f prime of -1. Now, if you remember, if a function is differentiable, then it is continuous. Now, if they're asking us for the derivative, it does not imply that the function is continuous. In fact, if we were to look at, let's just say the slope as x approaches -1 from the left side, the derivative here is simply just 2. And what I'm doing is I'm taking the derivative of this polynomial, which is 2. If we're looking at the slope as x approaches -1 from the right side, the derivative is -2x. And if we're evaluating this at x is equal to -1, then our slope there is actually 2. Now, what you're seeing here is that the slope on the left of -1 and the slope on the right of -1 is the same. However, we have not confirmed that it's continuous. So if it's continuous, our derivative is is positive 2. If it is not continuous, then there is no derivative that can exist because continuity is necessary for us to be able to at least start to analyze a derivative. Now let's say that we have a continuous function, but it's a sharp corner. Okay, well that's a different story. The derivative would not exist at a sharp corner, but let's at least start with continuity. So first off, if you remember our checklist from last chapter, we have f of -1, which is going to be the second function there. So we have the quantity -1 squared plus 6. So that gives us -1 plus 6, so we get 5. Now let's take a look at the limit. So we do need to do this in parts. So if we have the limit as we approach -1 from the left, we have 2x plus 5 as our function, and we get 3. That's going to be a problem. And then we have the limit as x goes to -1 from the right side, which again we just did because of the function value there. We get 5. This means that the limit as x goes to -1 of f of x does not exist. And therefore, this particular function is not continuous. And so we are unable to evaluate the derivative. This derivative would be non-existent. Okay, let's move on to the second page. All right, in the second page, for example 3, we have for what values of x does the graph of y have a point of inflection? So remember, we want to find the second derivative. So our first derivative is here, and then we have our second derivative. And again, this is just a bunch of polynomials, and that was one of the, again, this lesson on polynomials and exponential functions. So we're just reviewing those derivatives. Okay, with a point of inflection, we want to look at when the second derivative is equal to 0 or when the second derivative is undefined. But we also have to analyze that the second derivative changes sign at that value. So let's set this equal to 0. Let's factor out a 60x squared, and we get x plus 2, which means that our critical points would be x is equal to 0 and -2. Now we're going to put this on a test line, and remember, we're testing the sign change of y double prime. And I always label which function we're testing. I've mentioned this in some of the other videos, but you can do a graph of this actually really quickly, because if you look up at the blue equation, this is a cubic function with a positive leading coefficient. So the behavior of this particular graph is going to be some sort of cubic behavior like this. You have to kind of look at it one step further though, because when you factor it, we have x squared here, which would imply a double root, and -2, which is a single root, just based on the power. So our particular graph is going to look something like this for the second derivative, where it's going to sort of bounce off of here as a double root. What this means is that we have a negative sign up to -2, and then it is positive for the remaining portion of the second derivative. You can certainly test points. You can test values in the intervals, but I think that if you can sketch it, that's going to save you a lot of time as you work on these exams. So what are we looking for a point of inflection? Well, again, we're looking for critical points when the function equals 0, the second derivative function equals 0 or is undefined, but also a sign change. So in this case, the only time that we have those conditions applied is for x is equal to -2, which is option B. Okay, let's move on to example 4. So example 4 is just a straight kind of skill problem. We're just taking the derivative of an equation, excuse me, using the power rule. So we have -8 x to the -3rd plus 1/2 x to the first, and then derivative of 4 is of course 0. And then we're going to just simply plug in 2. We have -8 times 2 to the -3rd plus 1/2 times 2, and that gives us -1 plus 1, and so we end up getting 0 for this particular derivative. All right, let's do the very last question in this particular section. So we have a function f, and we want to know when does it have a relative minimum. So the first step is obviously to take the derivative, because what we're going to look for are all critical points. So we're looking for when the derivative is 0 or undefined. And so we're going to use the power rule here. 9 times 2/3 is going to be 6 times x to the -1/3 power. And then we have plus 3. Okay, let's go ahead and rewrite this because I think it's going to help us a little bit. So this is really 6 divided by x to the 1/3 power plus 3. Now the reason that that's helpful is because immediately we should see that one of our critical points is x is equal to 0, because that causes the function to be undefined, or the derivative to be undefined. So then the next one is that we want to look for when is the derivative equal to 0. And this is just going to be a little bit of algebraic manipulation. So we have -3 equal to 6 over x to the 1/3 power. And what we get out of this, if we were to cube both sides, is x equal to -8. So we have two critical points, x is equal to 0, and then x is equal to -8. So let's put this on a test line. Now remember, we're going to look for a relative minimum on the graph of f of x, which means we're looking for a sign change of f prime to be from negative to positive. So let's plot out -8 and 0. I can't, in the previous question, or excuse me, 2 questions ago, I was talking about how you could sketch a particular function. It saves you lots of time. This one would be difficult for me to sketch. I mean, I know at 0 there's going to be some sort of vertical asymptote. I know at -8 there's an x-intercept. That's kind of all that I know. So I think testing values is going to be your best bet. So if you were to test something to the left of -8, like you could pick, for instance, -27, just because when you would plug it in, you are taking the 1/3 power, which is possible for -27. But either way, again, we're plugging this into our derivative. So if we put in -27, and we would multiply by 6 and add 3, -27 to the -1/3 power is going to be -3, and then the negative power, so that'd be -1/3 times 6 is -2 plus 3. So we end up getting a positive value here for -27. So that just means that entire region would be producing positive values. Now in between -8 and 0, and we would sort of have to ballpark this a little bit, although I suppose we could pick, for instance, -1, and we would plug that in. That's going to be pretty obvious that's going to be negative. And then anything to the right of 0, that's going to be pretty obvious too. We could plug in anything there, and it's going to be positive. So what we have then for a relative minimum on the graph of f is, again, a sign change from negative to positive, which is going to be at when x is equal to 0. Okay, that does it for section 3.1. Thank you.